Greetings. I'll get started once we have up over 25 concurrent viewers. Waiting for at least 25 concurrent viewers. Oh, we're going the wrong way. All right. I think I'm going to go ahead and get started even though we're not at 25. Okay. Good morning. This is Friday's lesson. Last time we learned our last tidbit of information about motion graphs. So we basically have the following facts. We have two types of graphs we learned about. We learned about position time, and we learned about velocity time graphs. And the facts that we learned are that if you have a position time graph, slope is velocity, and bendiness is acceleration. Okay. For a velocity time graph, slope has a different meaning. So it was really important to look at the axes of the graph in order to understand how to interpret it. Slope is acceleration. And last lesson we learned about this concept of area under the curve, which is in a velocity time graph is displacement. Okay. So today we're going to kind of move on from velocity time graphs. We're always going to have that in the back of our mind. But we're going to talk about something called uniformly accelerated motion. And uniformly accelerated motion means that the acceleration is constant. Okay? The acceleration is unchanging. if you know, I want you to type into the live chat, what would a velocity time graph look like if it's representing uniform acceleration? Okay? What would a velocity time graph look like if it's representing uniform acceleration? Let me give you some examples where the acceleration is not constant. What if you're in a car and you push the gas pedal down? That's going to cause your speed to increase. You're going to accelerate. Okay? If you then take your foot off the gas pedal and you go to the brake, then your acceleration is going to change. It's going to go from positive to negative. Okay? So that would be an example of non-uniform acceleration. Another example would be if you're on the freeway, you push the gas pedal down and you achieve one acceleration, but then midway through you push the gas pedal down further, your acceleration, your rate of increase of velocity is going to then increase. So you have two different accelerations. But it so happens that oftentimes the acceleration is constant, or it can be thought of as being constant for a certain interval of time and then switching to another constant value. Okay? So I see some responses in the live chat that are correct, that if you have a uniform acceleration, your velocity time graph is a straight line. Okay? It should be a straight line. The slope of that line is the acceleration. If you have a non-uniform acceleration, your velocity time graph is going to look maybe like this. See, this has two different slopes, so that would be non-uniform acceleration. Or it could be bendy. If you had a velocity time graph that looks like that, the slope is changing. It's getting steeper, so that would be non-uniform acceleration. So this is what we are going to study today, is uniformly accelerated motion. And we're going to get a couple of equations, okay? Before I go any further, I want to think about what is the meaning of y-intercept. In math class, the y-intercept is where a line crosses the y-axis, okay? So if you think about it, we have a velocity time graph. So we're kind of talking about the v-intercept. So what is the meaning of the v-intercept? So I can see in the live chat, yeah, it's so what we have here is where this is time 0. So where this line crosses the v-intercept, the v-axis, is where the is the velocity when time is 0. So this is the initial velocity. Okay, so that is the meaning of the y-intercept in a velocity time graph, if you will. Okay, so we're going to derive 3 equations based on this. All right. So the first equation is simply an expression of the fact that this is a line. So the equation of a line in your math class is y equals, let me put a star there to indicate that this is the topic of today's lesson. The equation of a line in your math class is y equals mx plus b. All right, but let's convert that to the context of this particular graph, okay? So instead of y is what is on the vertical axis. We have velocity on the vertical axis. Okay, I'll put v final for final velocity. M is the slope, and we know that the meaning of slope in a velocity time graph is acceleration. On the horizontal axis, we have time. So instead of x, we have time, so we have at. And then, as I just said, b is the y-intercept, right? So, and we were just talking about how the intercept in this graph corresponds to the initial velocity. So, okay. So this is our first equation for today. And it's simply a restatement of the fact that uniformly accelerated motion has a linear velocity time graph. Okay. The second equation of motion is an equation for the displacement. So who can remind me, how do we get the displacement of a velocity time graph? Okay, type it into the live chat if you know. And while I'm waiting, I'm just going to talk about this. If the width of this line is t, then the height, this distance right here, would have to be at. All right? And the reason for that is the slope is a. So if we think about rise over run, it would be at over t. Those cancel out, and you just get a, the acceleration, okay? So this line goes over a distance t, and it goes up a distance at. All right, so I can see that many of you typed in area. Excellent. Area under the curve. All right, so let's calculate the area under the curve. You can see that when I say area under the curve, it's the area of this trapezoid. I'm going to think about the area as a rectangle. So this rectangle, okay, and then this triangle. All right, so the displacement is equal to the area of the rectangle plus the area of the triangle. So I'm going to go ahead and put the dimensions on here, okay? The width of this rectangle, it goes from 0 to t. And the height of this rectangle, you can see that because the intercept was v naught, this distance right here would be v naught. Okay, it goes from 0 to v naught. So this is a rectangle that has dimensions t by v naught. Okay. Now we go to the triangle. The width of the triangle is also t. The height of the triangle is only this distance right here. That's the height of the triangle. And while I was waiting for your responses, I was talking about how the height has to be at. Why? Because that would give rise over run equal to acceleration, which is what the meaning of the slope is, okay? All right, so we have the dimensions of these shapes, and now we just use the formula for the areas of triangles and rectangles, okay? So the area of a rectangle is base times height. So the area is going to be v naught times time. Okay. The area of a triangle is 1/2 base times height. So it's going to be 1/2 times base, which is t, times height, which is at. This distance is at. All right. Notice how we have t times t. So that is t squared. V naught t plus 1/2 a t squared. And I want to make sure you understand that the only the time is squared. Okay. All right. So that gives us our another equation. All right. So I'm going to write these down. These equations are called the kinematics equations. I'm going to write them down here, actually. The kinematics equations. Okay, and there are three of them. The first one is this displacement one. Delta x equals v naught times time plus 1/2 a t squared. All right, that's the first one. Remember, only the time is squared, not the whole thing. The second equation is this one. V final equals V initial plus AT. I swapped the location of the y-intercept. I put the y-intercept in front, so it's kind of like I wrote it as y equals b plus mx. That's normally how it's written in physics. And then there's a third equation, which comes from mixing these two equations together. All right. If you want to see the derivation of that equation, I'm not going to show it in this class because it's just a lot of algebra. But if you want to see it, I can show you during office hours sometime. Okay. So the third equation is V final squared equals V initial squared plus 2a delta x. Okay. These three equations are called the kinematics equations. Important point. You can only use these equations if the acceleration is a constant. If the acceleration is not a constant, then these equations won't be true. All right? So you have to always have that in the back of your mind when you're using these equations. Now, I would say 90% of the time in this class, the acceleration is going to be constant and these equations are applicable. Another thing I want to say is that you do not have to know these derivations, okay? I put the derivations in because I like to know why things are true. But I know not everyone in this class wants to be an engineer, wants to be a physicist. Not everyone wants to do that. So I have this in here for the people who are interested in going a little bit deeper, but it is not necessary to succeed in this class. You just have to know how to use the equation. Okay? Where's Camp Williams? Okay. One thing I want to point out is that each of these equations has 4 variables in it. 4 distinct variables. This first equation has displacement. It has initial velocity. It has time. It has acceleration. So this equation has 4 ingredients, and then time is again right here, but I already listed it, so I'm not going to list it again. Okay? So this equation has time in 2 places. That has 4 variables. Okay? The second equation has 4 variables. V final, V initial, acceleration, and time. The third equation has 4 variables. V final, V initial, acceleration, and displacement. Okay? So each of these equations has 4 variables. I want you to think about these equations as tools, okay? You can think about this as a wrench, right? A wrench is a tool that you use to solve a problem. And just like you have different size wrenches that work for a particular problem that you're trying to solve, you have 3 equations, you have 3 tools, and each of these equations is sort of tailor-made for a certain type of problem. That being said, they are all expressing the same thing. which is constant acceleration. They're just expressing it in different ways. So just like you would have a wrench that is the correct size to turn a nut, you have a physics equation that is right to solve a particular problem. Okay? So the rest of this lesson is going to be devoted to doing some example problems. Okay? And then we'll go to Zoom. Oh, we have a good question in the live chat, which is why is the height A and not, why is the height AT and not A? Well, the thing you want to think about with a line is that the further the line goes horizontally, the more opportunity it has to rise. So the amount that a line rises depends on how wide the line is, right? If you have a line that goes this far, is only that wide, it goes up that far. But if you have a line that extends the same trend but is wider, it goes up more. Okay? So the longer you let the line extend horizontally, the further up it has the opportunity to go. I hope that makes sense. Okay. So for our first example, a drag racer starts from rest. And completes a 400-meter long race in 9 seconds. What was the acceleration of the racer? So again, we are assuming that the acceleration of the drag racer is constant, which I think is a fairly reasonable assumption. It's probably not exactly constant, but it's almost constant. This is inspired by the racetrack. I live in Laverne, fairly close to the NHRA racetrack, and I can hear it. I can hear the drag racers very clearly from my house. And in fact, a lot of times there's sort of a hill next to the racetrack, and you can go to the top of the hill, and you can actually see over the fence into the onto the racetrack without having to pay to get in. You know, so I do that sometimes because I enjoy the sound of the racers as they zoom by, and it's like you can feel it in your chest. I find it very satisfying. Okay. So how do we solve this problem? Well, what we want to do is we want to parse the problem. Parse means you just sort of scan it for information. We're going to scan this problem for information that is going to help us solve it, okay? So a drag racer starts from rest. Starts from rest. That means that the initial velocity of the drag racer is 0. If you're in a race car and the initial velocity is not 0, we would call that a rolling start. Okay, so for example, in NASCAR, I think they often do rolling starts where it's the cars are already looping around, and then at a certain point they say, okay, we're starting the race now, and they start off with a non-zero velocity. It completes a 400-meter long race. So that means meters. That means that it's a measure of distance. So that means that delta x is 400. Okay. The race is completed in 9 seconds. Seconds are a unit of time. So the time for the race is 9 seconds. What was the acceleration of the racer? So So one of the four variables is going to be an unknown. So I'll say A equals question mark. Okay? So now what I do is I have these four variables, and I go back to my list of three equations, and I say which of the three equations has those four variables in it. Okay? So I will wait while you guys look at that and tell me which equation has those four variables. Very good. The first one. Excellent. So we're going to be using the first equation. So that is the correct tool for this problem. Okay, that's the right sized wrench. So here's what we do. We write the equation down. Delta x equals v naught t plus 1/2 at squared. And then we substitute in the numbers. Okay, delta x is 400. V naught is 0. Time is 9. Plus 1/2 times the acceleration. So the acceleration is an unknown. So the one that is an unknown, I'm just not going to replace. I will leave it as the variable. So A. And then t squared, so that would be 9 squared, which is 81. Okay? Now, generally speaking, if this wasn't our very first kinematics equation problem, I wouldn't even write this term because the initial velocity is 0. Okay, so I would just kind of say that's obvious, but I'm writing it out explicitly here. So when we go to the next line, we want to simplify everything. So 400 equals, so I'm leaving this term out because it's 0 times 9 equals 0. And then 81 over 2 is 40.5. All right, so this becomes a simple algebraic equation for acceleration. Okay, so I want to divide both sides by 40.5. And I get 9.9 meters per second squared is the acceleration. Okay? I think that's actually pretty realistic because, as I said, I go to the hill and watch the drag races sometimes, and they're usually completed in about 9 seconds, and I would say it's about 400 meters long, the race, so that's pretty accurate. I want to talk about what would happen I'm not sure I understand that question. It was 0.87, so I rounded that to 0.9. I could have rounded it up to 10.0. I just chose to do two significant figures. Okay, so what would have happened if you used the wrong equation? What if I had used V final equals V initial plus AT? What if I tried to use that equation? It would be pretty easy to see that you run into a problem. Here's why. So you'd say V final. Well, V final isn't in this list, so I have no choice but to leave it as a variable. V initial is 0, so I can just leave that one out. The acceleration is unknown, so I have to leave the acceleration as a variable. And then the time is 9. So that says the acceleration equals V final over 9. But that doesn't give me a numerical answer. You see what I'm saying? So I automatically know that this one is not the correct tool for this problem because I can't solve the resulting equation. So it's just like if you're using a wrench and the wrench isn't the correct size to turn the nut, You just go like this, and either nothing happens or you can't even fit the wrench over the nut. Okay? So it's not a big deal if you choose the wrong equation because it's going to become apparent in just a moment. All right. So let's do another example. A car is cruising at, let's say, 40 meters per second. That's quite fast. That's really quite fast. That's about 90 miles per hour. The driver sees a deer and brakes. Decelerating at 25 meters per second squared and coming to a stop. Okay? How far forward does the car roll while stopping? Okay? So, all right, so you might have experienced this before, all right? If you're in driver's ed, or if you have, or if you already have your driver's license, one of the things they teach you is you want to allow proper distance between you and the car in front of you, because what if the car in front of you stops suddenly? Okay? Then you have to stop. You have to decelerate. And you don't just come to a stop immediately. You roll forward while you're decelerating, okay? And so you need to have enough distance. The faster you're going, the more distance you need to stop, okay? So if I'm following someone down Indian Hill Boulevard, I can be a lot closer to the car in front of me than if I'm following someone on the freeway, okay? Because it's going to take me more distance to stop if I'm going at freeway speeds. All right. So let's go ahead and parse this problem for the knowns. It says a car is cruising at 40 meters per second. All right. That's what the car was traveling at before the brakes were applied. So that is the initial velocity. Initial velocity is 40 meters per second. The driver sees a deer and brakes, decelerating at 25 meters per second squared. So one thing we have to be careful about is the sign of the acceleration in this case. If the acceleration were plus 25 meters per second squared, then every second you are gaining 25 meters per second of velocity. So it would go from 40 to 65 to 90. So we have to have a negative acceleration if we're going to bring the velocity to 0 from 40. So the acceleration is negative 25 meters per second squared. So again, that comes from decelerating at 25 meters per second squared. Coming to a stop. So being at a stop means that you have no velocity, and that's the end of the problem. That's the end of the period of deceleration. So v final equals 0 meters per second. And then lastly, we have how far forward does the car roll while stopping? So we're asking for a distance, delta x. Delta x is a question mark. So I will wait again for the class to type into the live chat. Which equation are we going to use out of these three? Which equation is the right tool in order to solve this problem? can't be the second equation because the second equation has time. All right. And this problem doesn't want to know how much time does it take to stop. It wants to know how far forward do you roll while stopping. Okay. So we're going to use equation 3. So we have v final squared equals v initial squared plus 2a delta x. V final squared, that would be 0 squared. V initial is 40. So we have 40 squared plus 2 times a, 2 times negative 25. And then the acceleration is unknown, so I leave it in its variable form. Okay? So now our next step is to simplify this equation. 0 squared is 0. 40 squared is 1600. 2 times negative 25 is negative 50. So that's a fairly easy equation to solve. I would just add 50 delta x to the other side and divide both sides by 50. And I would get 32 as delta x. 32 meters. All right. So let me ask you this. What would happen if the deer was 30 meters in front of the car when the brakes were applied? There's a question. Will we have to memorize the kinematics equations? Well, I would assume that everything in distance learning is going to be open notes. I can't verify that you're using notes or not. And generally speaking, on exams, if we were in person, I let students use a note card with any equations for exams, so you don't have to memorize them. But again, it kind of depends on your level of interest, like what you're trying to do, what you're trying to get out of this class. If you're in this class and you're like, I'm going to be an engineer, I'm going to be a physicist, I'm going to do science, then I would recommend memorize them. But if not, it's no big deal. Okay? So yeah, what if the deer is 30 meters in front of the car when the brakes are applied? The car is going to roll forward 32 meters. So that means that the deer is going to get hit. If it doesn't move and you don't turn out of the way, it's going to get hit. So the deer is going to get splattered in that case. Actually, it might not get splattered because as the car is coming to a stop, it's slowing down, right? And because 30 meters is like almost to the point where the car has stopped, the deer might just get tapped by the car. Maybe hit, but not hit hard enough to where it's going to get killed, but we don't know for sure. If the deer is 40 meters away, then the car is going to stop in 32 meters, and the deer will be 8 meters in front of you when you come to a stop. All right, we'll do one more example, and then transfer to the Zoom room. A rocket, or I'm going to say a space probe, can accelerate at 30 meters per second squared. All right, that's a pretty typical acceleration if you're in space. Okay, if you accelerate too much, you risk damaging the structure, okay, of the probe. Similarly, if you have humans in the space probe, then accelerating too much would hurt them, as we saw in the video. So we're kind of limited on the amount of acceleration we can have. It increases its velocity from 1,000 meters per second to 2,200 meters per second. All right. How long must the thrusters be fired for? So this is actually a pretty realistic thing. I'm going to type a game into the live chat. It's called Kerbal Space Program. And in Kerbal Space Program, it's a sandbox engineering game where you can build rockets and you can launch them into space and so on. I think it's about $30 on Steam. Would highly recommend it if you have $30 to spend. And one of the things you do in the game is you push a button to fire the thrusters. And the moment you push the button, the velocity starts to change. Okay, the probe starts accelerating. And then you push the button again, and the rockets stop firing. And basically what you do is you fire the thrusters until you achieve the velocity that you need to achieve, and then you cut the thrusters. And so, you might be trying to speed up if you're trying to escape a planet and travel to another planet. You might be trying to slow down if you're trying to land. So, but this is a very realistic calculation. It is important to know how long to fire the thrusters for to achieve the appropriate velocity. Okay. So, what is the information here? We've got 30 meters per second squared. That's the acceleration. Okay. We have the velocity goes from 1,000 to 2,200. So that means that V initial is 1,000 meters per second. V final is 2,200 meters per second. All right. And then we're trying to get the amount of time that the thrusters are fired for. So T equals question mark. Now, if you haven't guessed already, I'm doing one example for each kinematics equation. So this is the third kinematics equation. We plug in variables. V final is 2,200. V initial is 1,000. Acceleration is 30. We can solve this equation for time. And I'm not going to show the steps because my lesson is running a little bit long, but the time is 40 seconds. Okay? So that would be a 40-second burn of the thrusters, and then you would achieve the velocity that you need to. All right, so that's my lesson for today. And I will meet you in the Zoom room. Have a nice day.